look at converting between mass, moles, molecules, and number of atoms. And we're going to first take a look at converting between mass and moles. So to do this, we're going to use the molar mass as a conversion factor in the method called dimensional analysis. So if you remember, molar mass is the mass of 1 mole, and we can find it for something like H2O by looking up the atomic masses and adding them up. So H2O, for example, would have a molar mass of 18 grams per mole. Then 18 grams is the mass of 1 mole. So we can use this as a conversion factor to convert between mass and moles. So let's say we're starting with mass. Then I would want to use this as a conversion factor by putting moles on top and grams on the bottom. And I can use the fact that 18 grams are equivalent to 1 mole as long as I'm working with H2O. If this were a different substance, I would have a different molar mass other than 18. But I can use whatever the molar mass of that formula is to convert between grams and moles. If I'm starting with grams, grams would cancel out and I'd convert it to moles. These are equivalent quantities, but with different units. Or if I was starting with moles and I need moles to cancel out and put moles on the bottom, then I would put the 18 grams on top. 1 mole is equivalent to 18 grams for H2O, as long as I'm dealing with H2O. So just notice that the value for molar mass is always next to the grams in the conversion factor, and 1 is always next to the moles, because 1 mole weighs the molar mass in grams. Okay, so let's take a look at an example. Calculate the number of grams and 0.455 moles of calcium carbonate. So I'm starting with 0.455. I'm going to write my number and my unit. Be very specific about your unit. You might even want to write moles of CaCO3 to be specific. And what I'm going to notice is I want a conversion factor that has moles on the bottom so that moles cancel out and has grams on top. Well, what has the units grams over moles? That is the molar mass. So just somewhere on the side or in my calculator, okay, I should find my molar mass. There's 1 calcium, there's 1 carbon, there's 3 oxygens. Adding it all up gives me about 100 grams per mole. Okay, 100 is going to go next to the grams, and that's the mass of 1 mole. Moles will cancel out, and in my calculator, I'm doing 0.455 times about 100, and I get 45.5. And you're going to notice that I'm going to try to be very careful about keeping the correct number of significant figures. We typically don't use conversion factors to guide our sig figs. We want to use our starting measurement. So there's 1, 2, 3 significant figures to start with. So I want to keep 3 significant figures in my final answer. Take a moment, try the next example, and check your work. Notice here I give a name instead of a formula. Carbon tetrachloride is CCl4. And if you write a different formula, that's going to impact your molar mass and your answer to the problem. So I'm going to write 2.59 moles to start with. I'm going to notice that I want moles on the bottom to cancel, grams on top, and I can go between grams and moles using the molar mass. So somewhere in my calculator on the side, I can add up to find the molar mass. 154 grams in every 1 mole. Remember that molar mass goes next to grams, 1 goes next to the moles. I want moles on the bottom to cancel, and I'll notice I'll be left with grams. I'm going to keep 3 sig figs. Take a moment, try this example. In this example, I'm starting with 62.70 grams, and I want my conversion factor to have grams on the bottom so that they cancel, and moles on top. So now when I do my molar mass, and again, make sure you get the correct formula. Copper has a 2+ charge, sulfite has a 2- charge. They cancel out to give me CuSO3, and I can add up all their molar masses. I get about all their masses to get the molar mass. I get 143.6, and that's going to go next to the grams in the bottom. Now I'm dividing by it because I want grams to cancel out. 1 mole on top, and I get, keeping 4 sig figs, about 0.4366 moles. In case you need to double check your conversion, on the AP equation sheet you do have this calculation or this equation written where N is the number of moles, M is the mass, and capital M is the molar mass, in case you forget how to do this, but it's just much easier to do this with dimensional analysis rather than plugging into an actual equation like this. This is under gases in your equation sheet. Okay, now that was one fact about the mole, that 1 mole has a mass of whatever the molar mass is for that compound. The other fact about the mole is that 1 mole is equivalent to 6.022 times 10 to the 23rd particles. So out of that equality, 1 mole equals 6.022 times 10 to the 23rd things, I can make another conversion factor. And depending what I'm starting with will depend where the 6.022 times 10 to the 23rd goes and where the 1 mole goes. Now, you might say, okay, when do I use molecules? When do I use the word atom? What does particle really mean? So if I'm talking about a monatomic atom, okay, or monatomic element, I should really say, because monatomic atom kind of means the same thing. Mono meaning one, atomic atom. So elements that are not diatomic, essentially, so something like carbon, something like copper, something that is not one of my Hofsprinkles, then 1 mole is equivalent to 6.022 times 10 to the 23rd atoms. So like 1 mole of copper, there's 6.022 times 10 to the 23rd copper atoms in that mole. If I'm talking about a molecular compound, so that is these are different molecules, something like H2O, or my diatomic elements, things that are made up of more than one atom joined together, that's when I'm using the term molecule. So 1 mole of H2O contains 6.022 times 10 to the 23rd H2O molecules. 1 mole of Cl2 contains 6.022 times 10 to the 23 Cl2 molecules. And if I'm talking about an ionic compound, we don't really use the word molecule, so you might see the term formula unit or unit thrown in instead of molecule. So for instance, 1 mole of NaCl, that's an ionic compound made of metal and nonmetal, contains 6.022 times 10 to the 23rd NaCl formula units. Because again, we don't really use the term molecule because it's not made of molecules. Okay, so now that we just got some of that terminology, let's actually practice some examples. Take a moment, try this. How many atoms are in 2.5 moles of sodium? So I'm going to write the 2.5 moles of sodium to start with. And again, like I said, I like to be super specific about my unit, not only moles, but moles of what? Moles of Na. Why is this important? Because eventually I might be in moles of something else, and this will help guide my conversion factors. So 2.5 moles of Na, if I think about my conversion factor, I want moles on the bottom and I want number of atoms on top, and that's when I'm using that 6.022. There's 6.022 times 10 to the 23rd atoms in 1 mole. And in my calculator, I would do this, and I would get 1.5 times 10 to the 24th sodium atoms. Okay, what if the question started with 2.5 grams of sodium? Then I wouldn't be able to use this conversion factor right away. I would have to mole it out. So remember that you're always going to have to go through moles when converting. So typically when in doubt, I always say mole it out. If you start with grams, first turn it into moles, and then you can turn it into number of atoms or number of molecules. But these are your conversion factors that you should memorize. 1 mole is equivalent to 6.022 times 10 to the 23rd particles, and it's also equal to the molar mass in grams, and that's how we can get these conversion factors. Take a moment, try this example, and then check your work. Okay, recommended daily intake of sodium is 2.5 grams. How many sodium atoms are in this sample? Okay, so I'm starting with grams. I want to eventually get into the number of atoms. When in doubt, mole it out. I'm not sure how many atoms are in a certain number of grams, but I do know how many atoms are in a certain number of moles. So what I can do is I can first mole this out, convert this into moles, and then I can convert it into the number of atoms. So to convert it into moles, that's when I'm using the molar mass. I want grams on the bottom so that grams cancel, and I want moles on top. And I'm just being very specific about my unit. Grams are moles of what? Grams are moles of sodium, Na. And I put the molar mass next to grams. I want on the bottom, so grams cancel. I put 1 next to moles on top because 1 mole of sodium weighs 23 grams. Now grams cancel, and I'm left with the unit of moles. Now I can convert moles to number of atoms. This is just a monatomic element, so 1 mole of sodium would contain 6.022 times 10 to the 23rd atoms. I want moles on bottom so they cancel, and I want atoms on top. So in my calculator, I'm doing 2.5 times Avogadro's number divided by 23, and I should get, keeping 2 sig figs, 6.5 times 10 to the 22 Na atoms. Okay, take a moment, try this example. Similar to last example, okay, I have 100 grams and I need number of molecules. I don't know offhand how many molecules are in a certain number of grams, but I do know how many molecules are in a mole because that's Avogadro's number. So when in doubt, mole it out. Let's change this into moles using the molar mass, so somewhere on the side, calculate the molar mass, about 114, and that's going to go on the bottom, so grams cancel, and 1 mole is on top. Now I can change moles into the number of molecules by using 6.022 times 10 to the 23rd, Avogadro's number. Notice Notice now I'm not using that's how many atoms, I'm using that's how many molecules, because C8H18 is a molecular compound. So it's not how many atoms of it I have, it's how many molecules I have. And I should get, rounding to 3 sig fig, since that's what I start with, 5.28 times 10 to the 23rd. Now what you might see is, okay, this is the number of molecules. What if for a molecular compound, it asks me for the number of atoms? So let's say in this last example, how many atoms of carbon are in this number of molecules? So that's when I can use the subscripts as conversion factors. For every 1 molecule of C8H18, I have 8 carbons. So if this is how many molecules I would have 8 times the number of carbons. Or if it was asking about hydrogen, I'd have 18 the number of hydrogens. So all I do is, here's that number of molecules from the last example. Okay, I'm using the subscripts as a conversion factor. There are 8 carbon atoms for every 1 C8H18 molecule, and the molecules would cancel out, and I'm left with atoms. And this is why I said I like to be super specific about my unit, and this is really going to help guide what my next conversion factor might be. Now I'm changing from molecules into atoms. And keeping 3 sig figs, here's my answer. Notice it's 8 times the amount. So as a note, you can use the subscripts to convert between atoms of an element and molecules for these molecular compounds. Take a moment and give this one a try. How many hydrogen atoms are in 30 grams of heptanol? And I didn't write here what the formula of heptanol is, but here it is. It's not something you have to memorize. Okay, so giving this a shot, I don't know offhand how many hydrogen atoms are in every gram here, but let's, when in doubt, mole it out. Let's first change it into moles. I can do that using the molar mass. It's 116. That goes on the bottom, so grams cancel out, and I'm left with, and that's how many grams are in 1 mole. Now I'm in moles. I don't know offhand right now how many atoms, but I can go from moles into molecules, because I know that there's Avogadro's number, 6.022 times 10 to the 23rd, number of molecules in every 1 mole for this molecular compound. Now I want how many hydrogen atoms. So that's when I can use the subscripts as conversion factors, meaning for every 1 molecule, there is 16 H's. So I can say there are 16 hydrogen atoms for every 1 molecule. A molecule on the bottom, so it cancels, and I'm left with hydrogen atoms, which is what I want my unit to be. And I rounded to 3 significant figures. Take one more moment to try this example. Okay, now I'm starting with the number of hydrogen atoms, and I want to change it into mass in grams. So it's similar to the last problem, but going backwards. So I can use the subscripts as conversion factors to go from hydrogen atoms to the entire molecule, to scale upwards from atoms to molecules. So I want hydrogen atoms on the bottom this time because I want them to cancel, and I see that there's 28 hydrogen atoms for every 1 molecule of this testosterone. Now I'm in number of molecules. I can scale up to, or I can change it to moles by using Avogadro's number. I want molecules on the bottom, so Avogadro's number is on the bottom, and I want moles on top. And now I can change from moles into mass using the molar mass. Somewhere on the side calculated, it's 288 for this compound, and I didn't really have room to put it here, so I just put it right here. I want the molar mass on top, so I'm left with grams, and I want moles on the bottom so that they cancel. And I will get 0.0663, keeping 3 significant figures because these leading zeros are insignificant. Just as a note, if you are dividing by 6.022 times 10 to the 23rd in your calculator, I find it helpful to use that E format. So you would write 6.022, and if you're using a TI-84, you're just pressing, I think it's second and the comma button, and you'll see above that there's like this little capital E to get this E, and this E stands for times 10 to that. So all you have to do is, if you're putting this E in, you just write the coefficient, 6.022, then you write E, and you put whatever the exponent of the 10 is. You don't have to write times 10 to that. If you don't do that format, then you have to make sure that you enclose that entire Avogadro's number in parentheses, just to make sure that your calculator is dividing by this whole number. instead of dividing by 6.022 and then multiplying by 10 to the 23rd after. So just make sure your calculator is doing the correct order of operations by either putting in parentheses or using that E format, or you can even program your calculator to have 6.022 times 10 to the 23rd stored as a certain symbol if you prefer to. Take a moment to try this problem and then check your answers. So we can actually do this problem without our calculators and without actually calculating values, which might be helpful to practice for like the multiple choice component of the AP exam, which doesn't require a calculator. So I'm just showing out the dimensional analysis, which is always a great starting step if you are trying to do math without a calculator, because you might see the way things can simplify or ways around doing out the calculation. So here's my 3 setups. Notice that they look almost identical. They're all starting with 100 grams. The only difference is their molar masses, and then to turn into atoms, it all is the same number, Avogadro's number, to multiply by, because that's how many atoms are in a mole. So it's essentially going to boil down to which one of these has the most moles. That would give me the greatest number of atoms. And to have the most moles, I would want to divide by the smallest number, the smallest molar mass. Magnesium has the smallest molar mass, so I'm dividing by the smallest number here. That's going to result in the largest answer, the largest number of atoms. So magnesium would be my answer here. And that's allowing me to get out of actually doing any calculations here. And you might have actually just been able to think about this logically without even seeing out the dimensional analysis. And that is a great thing to do as well. Take a moment, try this one. This you can also do without a calculator. Let's just look at the setups here. So again, very similar setups. This time they're all starting with different masses and they have different molar masses, but the final step is all the same because changing moles into number of atoms would be the same for all these different monatomic elements. Now, here is the same number, so this would be about 1 mole, right? Dividing 107 by itself would give me 1. So this is about 1 mole of silver. The zinc, the 70 grams of starting mass, is greater than the molar mass. So this is going to give me a number that's greater than 1 mole. And the magnesium, the starting mass is less than the molar mass. So this is going to give me a number less than 1 mole. So if I know silver has 1 mole, zinc is greater than 1 mole, and magnesium is less than 1 mole, then I can just automatically rank them. Zinc would be the most, then silver would be after that, and then magnesium would be the last.